Welcome back, everybody. Are there any questions before we get started? Okay. So we're in chapter 4 and almost finished with the first slide deck. I believe last time we met, we proved this theorem, fundamental theorem for contour integrals. And I had a number of typos in this one. I hope that I've fixed those. By the way, the slide decks have been updated 5 minutes before class, 10 minutes before class. So go grab the latest copy from Canvas. I'll be updating those later on GitHub. So in case you are interested in downloading them from GitHub, they'll be there later on. The lecture notes have also been updated. Sometimes the lecture notes and the slides are a little bit out of sync. If you ever see any inconsistencies, kindly let me know and I'll be glad to update those and fix them. Oops, let's see here. There we go. Okay, so we proved that fundamental theorem for contour integrals last time. We proved this corollary as well, stated and proved this, that says that if D is an open bounded path connected set and F is an analytic function on D and has the property that the derivative of F is equal to 0 at every point in D, then F is a constant function on D. So we proved that one as well. And let me state this theorem without proof, but we can, most of what we've set up allows us to prove this, but I just decided not to include the proof in the book and in the slides, just so we don't have to prove everything. So this theorem is an equivalence theorem for path independence. Suppose that D is an open bounded path connected set and F is a continuous function on D. So now we're not assuming that F is analytic or anything like that, just a continuous function. Then the following properties are equivalent. All right, so that means that 1 implies 2, 2 implies 1, 1 implies 3, 3 implies 1, and 2 implies 3, and 3 implies 1. They're all equivalent to each other. So I can replace any of these statements with any of the other ones. The first statement is that integrals are path independent. And what we mean by that is that if we have any 2 points, Z1 and Z2 in the set D, and any 2 contours, gamma and chi, that connect point Z to point Z1 to point Z2, then it holds that the integral over the first contour is equal to the integral over the second contour. And the idea is if we have path connectedness, or sorry, path independence, that means if I have one contour going from Z1 to Z2 like this, and then I have another contour, can even cross, going from Z1 to Z2 like that, then we say that these things are path connected if and only if, or sorry, path independent, if and only if it doesn't matter which contour I take to get from Z1 to Z2, I'll calculate exactly the same integral. So that's the first statement. Integrals are path independent. That's equivalent to the statement 2. Integrals around closed contours are 0. So if we have path independence, then we have this property as well. All right. In other words, if gamma is any smooth closed curve in D, contour in D, then the integral over gamma of F is equal to 0. So it's easy to see that if I have this, I'm going to have that, and vice versa. How? Well, I can take these 2 contours here and let's rename them gamma 1 and gamma 2. And let's define a new gamma to be equal to, first you do gamma 1, and then you do gamma 2, but in reverse order. Okay, so that gives you a closed contour. So let's start by assuming this first. Well, then I can go around this contour in this way. First, you do gamma 1, and then you do gamma 2 in reverse. That gives you a closed contour. So we know that closed contours have this property, okay, that the integral over closed contours are 0. But that means by splitting up the integral into two separate integrals, that this integral must equal that integral, based on some other properties that we had earlier in the chapter. Okay, so the equivalence of these two is pretty straightforward. This one's a little bit harder, but you can use the theory of the last two theorems, last theorem and last corollary that we just learned. So there is an antiderivative for f in D. In particular, there's a function capital F. So we're working with little f as our base function. Capital F that is analytic on D and has the property that f prime of Z is equal to little f of Z. All right, so all three of these properties are equivalent. If I have one, then I have the other two. Okay, and another way of putting it is that 3 implies 2, 2 implies 3, and so on. They're all equivalent. So again, I state that without proof because you can use the theory that we built up to prove that fairly easily. That's it. That's the first slide deck for chapter 4 finished. And so now we're into the second slide deck. And this will finish out the chapter 4 for us. Now, all of this work that we've been doing is leading up to two sections that I want to spend maybe one class on each. So the method of steepest ascent and the saddle point method. That's because these are fairly sophisticated methods that use contour integration. In fact, we'll learn that the method of steepest ascent and the saddle point method are nothing more than Laplace's method in disguise, where we use these contour integration theory to transform one integral into another, and then use Laplace's method. I'm getting a little bit ahead of myself because before we get to the method of steepest descent and the saddle point method, these two new techniques for doing asymptotic expansions of integrals, I have to talk first about Cauchy's theorem and Cauchy's integral formula. All right, so this is part 2 of 2. And the chapter, of course, is titled Contour Integration in the Complex Plane and the Method of Steepest Descent. And you might say, well, why not also list the saddle point method? And that's because the saddle point method is really just a kind of method of steepest descent. These two are really more or less the same. All right, so the next section that we're going to go into is discussing Cauchy's theorem and Cauchy's two integral formulas that we want to use. So let's talk about Cauchy's theorem. So this is a famous theorem that you've seen if you've taken complex analysis before. You may have seen it in other courses like in mathematical physics or mathematical methods for engineers. It's fairly important for all of physics and engineering and many other sciences as well. We're going to state and prove a simplified version of Cauchy's theorem first, and then we're going to state without proof a more complicated version that in a complex analysis course, you may spend maybe 2 weeks trying to prove. The simplified version gets proven with two very simple calculations, okay? One involving Cauchy-Riemann theorem, Cauchy-Riemann equations, and then the other one involving what's called Green's theorem, which we covered in a previous lecture. Okay, so without further ado, here's the statement of the theorem. Suppose that D is an open, bounded, simply connected set in the complex plane, and F is analytic on D. So our definition of analytic that we're using in this class is that analytic means it's a differentiable function, okay, in the complex sense. Just one times differentiable. It's going to turn out that if it's one times differentiable, it's going to be infinitely differentiable on a set. Assume additionally that f prime is a continuous function. So the derivative exists. We're going to assume additionally that f prime is a continuous function. So what does it mean for a complex function to be continuous? Well, you can view it, there's a couple of different ways to view it, but you can view it in the following way. You can view it as the real and imaginary parts of f are continuous functions in the sort of real sense. That's one way that you can view this. And so this is going to be a particular importance to us when we go to apply Green's theorem, this additional assumption here. Suppose that gamma is a smooth, simple, that is non-self-intersecting curve that is counterclockwise oriented and, if I haven't said it already, closed. So that means we're looking at curves that basically look like this. Okay, counterclockwise oriented, meaning that I'm going anti-clockwise. It has to be simple, so you can't have crossing points, so no figure 8 type of curves like this. And let's see what else. It has to be a closed curve. That means you can't, we're not looking at any curves which have this property, where they don't quite meet up, okay? So we're only looking at curves like this, where their start and end point are the same. And by the way, they're simple in the sense that they start at a point, go around, and they end on the same point. They can't keep continuing around again. Okay, we're not going to run that curve around twice. If all of these assumptions are satisfied, then the integral of f over this contour gamma, this contour is contained in this set D. Then the integral of f around this contour is always just equal to 0. Okay, questions about that?
I have a question.
Yeah.
So we assume f is analytic. Why do we need to assume f prime is continuous? I think if f is analytic, then automatically it has infinite many derivatives and they must be continuous.
Yeah, but we don't know that yet. So we're going to prove that, right?
Oh.
Right, but we don't know that yet. Actually, this the fact that it's 1 times differentiable, or sorry, means that it's going to be infinitely differentiable and therefore smooth. But we don't quite know that yet.
Oh.
Yeah. So let's break this contour integral up into real and imaginary integrals, right? Contour integrals. And this is something that we talked about in the last class and the class before. So if I write u as the real part of f, by the way, whenever I write this by hand, I usually, instead of writing this complicated script R, I'm going to write RE. That means the real part of z. So if z is equal to x plus iy, then what is the real part of z? It's just equal to x. And the imaginary part, I'm going to, when I write it by hand, I use this symbol rather than this symbol. This is an I and this is an R in the calligraphic, no, so in the math fractor typeset in math, in LaTeX. I'm going to use this when I print by hand because I can't make symbols which look like that, okay? The imaginary part of Z is, of course, just Y. So that's what those symbols mean in case you haven't seen them or haven't seen them in a while or haven't thought about them in a while. We proved in an earlier lecture that the integral of f over this contour can be written as the real contour integral. So this is a bold-faced gamma, so this means our realification of gamma. You just turn this complex curve into a real curve by just thinking about it as a vector. It's the integral of over this vector function, or this vector contour gamma, of u dx minus v dy. All right. And plus the complex unit I times this real contour integral. Okay, so we break this, imagine this complex contour integral into 2 real integrals. And now we're going to operate on this using Green's theorem. Now, before we do that, let's define a set. let's define this set D sub gamma, which is a set inside of D, whose boundary is the image of gamma. Okay, so the boundary of D gamma is the image of gamma. So basically what we mean here is that this is our D gamma. Okay, it's the set bounded by gamma. Remember, gamma is a counterclockwise oriented curve. And the way you can remember, well, is D gamma inside or outside of gamma? We use what's called the right-hand rule, right? If you use the right-hand rule, then your fingertips curl in the direction of this curve. Your thumb points up out of the page, and the inside is defined as the inside with respect to that right-hand rule, okay? Everything on the left-hand side of that curve as you traverse it. Okay, so that's D gamma. Then by Green's theorem, the reason why we're using this extra little bit of information here, Calvin asked, why are we assuming this? Isn't it already true? Well, we don't know that yet because we haven't gotten that far in the theory. So we're assuming this is extra little bit of information that we think is going to help us. What happens if f prime is a continuous function? Well, that means that these partial derivatives, dv dx and du dx and du dy and dv dy are all going to be continuous functions. Okay? Continuous real functions. So by Green's theorem requires that these partials have to be continuous. And we're using or allowed to use Green's theorem because of this extra added assumption. That's why that's in there, okay? So because of that extra continuity assumption, we know that the partials are all going to be continuous and we can apply Green's theorem. We apply Green's theorem, which says that for this real contour integral, we just replace the contour integral by an area integral over d gamma of this integral involving partial derivatives. But now the Cauchy-Riemann equations kick in and say that this guy is exactly opposite in sign and equal to this one. So the integrand turns out to just be 0 by Cauchy-Riemann theorem, okay, or Cauchy-Riemann equations. So you integrate 0 over any set d gamma that you like, and you get 0. And similarly, for that second integral, this guy, okay, we don't have to worry about the I in front of here because we're going to show that this whole integral here is just 0. So I times 0 is still 0. So it's this guy we're interested in. Well, if we can use Green's theorem again, which we can because these partials are continuous, we just get this integral. We trade this contour integral for this area integral over the set d gamma. But again, by Cauchy-Riemann equations, this is equal to that, but opposite in sign. And so the integrand turns out to be 0 again. And so you integrate over 0, you get 0. So this is a simplified version and a simplified proof of Cauchy's theorem. So Cauchy's theorem is namely this statement. If f is analytic on a set D and you have a contour in D, which is oriented in the counterclockwise direction, then you will always get 0. Now, sometimes you'll see it stated as if you have this set D and you have any contour integral running clockwise or counterclockwise, we have a 0 result over the contour. And why is that so? Does anyone want to hazard a guess? So we know by Cauchy's theorem that the contour integral when we go in this direction is equal to 0. How do we know that the contour integral if going in the opposite direction is also going to be 0?
Is the work principle, like the work done is 0?
What's that? The work principle?
Yeah, like the work done.
It's related. It's related. It's a conservation property essentially. It's mathematic. I'm going for the sort of mathematical reason it's true. And the mathematical reason is if I run a contour in the reverse direction, then that's equal to minus the contour in the forward direction. It's the same, that's the same principle that we have with real integrals, right? If you integrate from a to b, then that's the negative of the integral from b to a. I keep wanting to write x, sorry. Okay, but we know by Cauchy's theorem that this guy is equal to 0, right? So this integral is also equal to 0. So it doesn't matter what direction you run the integral. Does everyone understand that? All that really matters is that you have analyticity inside in this region. It can fail to be analytic outside that region. For example, there can be a singular point somewhere out here, outside of this curve. And I'll show you why that is so with an example later. Does everyone understand that point? I can take this integral in the forward direction or in the reverse direction, and either case, you're going to get 0. And the reason is because it's inside of D, inside of this whole set D, we're analytic. Now, here's the more general statement of Cauchy's theorem, and you can see that I'm going to state this one without that assumption that the contour is going in the counterclockwise oriented direction. Suppose that D is an open, simply connected, bounded set, and F is analytic on D. For any simple, piecewise smooth, closed contour, gamma, the integral over gamma of f dz is just equal to 0. Now, we've left off a couple of assumptions that turns out you don't actually need. We don't need f prime to be continuous. We don't need that. And we already saw why you don't need the contour to be oriented in the counterclockwise direction. It's because if you find that it's 0 in one direction, it's 0 in the other direction as well. Now, for the application of Green's theorem, you really do need the contour going in the counterclockwise oriented direction. That's important for Green's theorem. All right. Suppose now we can start applying what we just learned, right? Suppose that D is an open, simply connected, bounded set, and F is analytic on D. Actually, we know this result because of the path independence equivalence result that we had on the last slide of the last slide deck. Okay, so we already know that because we have this result, we have path independence. But we can restate it anyway. Suppose that D is an open, simply connected, bounded set, and F is analytic on D. That gives us, by Cauchy's theorem, that we're going to have path independence, as we'll see. Suppose that Z0 and Z1 are arbitrary points in D. And suppose that gamma and chi are two simple piecewise smooth contours connecting Z0 to Z1. For some reason, I decided to use Z0 and Z1 rather than Z1 and Z2. Okay, so here's our Z0 and Z1, formerly Z1 and Z2. And one contour gets you there by one route, and the other gets you there by another route. Now, as long as they're both contained inside of D, where we're assuming that f is an analytic function, it doesn't matter which contour we use to get from Z0 to Z1, the result of the integration is going to be the same. And again, the reason is because I know by Cauchy's theorem that if I traverse this contour, chi, in this direction, and then I traverse gamma in the reverse direction, I get a simple closed contour. Okay. Now you might worry what happens if these two contours cross, because then you have a contour which is no longer simple, right? So what happens if I have another contour, let's say given by this red curve? So instead of gamma, now let me draw another make another drawing entirely. So suppose I have Z1, Z0 inside of my new set gamma. F is analytic on D. Or sorry, I said gamma, but I meant to say D. Suppose I have one contour which connects Z0 to Z1 like that, and I have another contour which connects them like this. They cross, and so when I make the composite contour, I no longer have a simple closed contour, right? Simple means that it can't intersect itself. So what do I do in that case? Well, I can make the contour like this. I can traverse it, this guy, right, like that, and then finally like this. So that gives me a non-simple closed contour. And what I'm going to do is I'm going to break that contour into two separate contours. Namely, I'm going to run this guy first. There's a closed contour. And here's another closed contour. Over both of those, I know that the result of given to us by Cauchy's theorem is that the contour integrals are both going to be 0, right? And so I can use that to reestablish this fact or prove this fact. So it doesn't matter. So you can state then, even though I said here, these are simple, piecewise, smooth, closed contours, you can drop this word simple. You can allow it to cross itself, as long as the number of crossing points are finite. Okay. Now let's do an example. You've probably been wanting to know how these contour integrals go. So here's a particular example. Remember, we already know how these should go because we know that you can convert complex contour integrations into real integrals. Suppose that gamma is a circular counterclockwise oriented contour of radius r around the point Z0. Then we can show that the integral around gamma of this function, 1 over z minus z0 dz is equal to 2 pi I. So why do I get a result which is not equal to 0? Well, because this function here is not going to be analytic inside of gamma anymore. So let's see this. So what did I say this contour was? This contour is, well, first of all, let's make a complex plane here. So here's our point Z0, say. And the contour that we're interested in traversing has radius r and it's centered on Z0. So that contour might look something like this. Let's see, there we go. Okay, so there's my contour. I'm gonna add some arrows. There we go. So there's my contour gamma. The radius here in real units is r. Okay, that means the modulus or the difference, the size and modulus of a point here and a point here on the circle is in modulus r. So now inside of this contour, the function f, which is this guy here, is no longer going to be analytic. It has a singularity here where it's not going to be differentiable. And that's why we're going to get something which is non-zero. All right, but let's prove that. To do this calculation, we need an analytic expression for the contour. And we can get it very simply as Z0 plus r times e to the it, where t goes from 0 to 2 pi. Now, you've probably seen this expression before, e to the it, right? And you've seen Euler's formula, e to the it is equal to cosine t plus I sine t. if you follow this around, then then this contour is going to start here and go around Z naught and finish here as well. Okay. So if you've never seen that before, you should confirm that for yourself, that the contour starts here, goes round Z naught, and ends back here, closes on itself. Okay, so that's that guy where t is between 0 and 2 pi. So by definition, our complex contour integral is equal to an integral of the type 0 to 2 pi. That is integral of t equals 0 to t equals 2 pi, 1 over this denominator, z naught plus r e to the it minus z naught. The z naughts cancel with each other. Okay. Now, all I'm doing there is replacing z by the value of gamma on the contour. So that's that part right there, given to us by that. And remember, by the definition, we had to have the derivative of this contour, okay, with respect to t. And so that's just going to be ri e to the it. Now, in case you haven't seen it before, what happens if I take the derivative of this guy? Well, this is just a real function. So let's go to another page here. Some of you haven't seen this before, so I don't mind doing it. So we want to take the time derivative of e to the it. All right, and I want to show that that's just equal to I e to the it. All right, so how do I show that? Well, this is just an ordinary derivative here, and we're going to use Euler's formula. That's cosine t plus I sine t. Okay, I hope we get it right. So what happens if I take the derivative of the cosine? That should be minus sine t. And what happens if I take the derivative of the sine? So that's going to be plus I cosine t. But notice that this is just I times cosine t plus I sine t. Does everyone see that? It follows from the fact that I squared is equal to minus 1, right? It's that weird unit that has that property. And then this, of course, using Euler's formula once again, this is just e to the it. And of course, I have this prefactor of I. Okay, so that's just, I've used the derivative of this function here. Okay, simple time derivative in this location. Well, now the z naughts cancel, and I just get ri e to the it over r e to the it. E to the it cancels, r cancels, and so I just have the integral from 0 to 2 pi of I. Of course, that just becomes 2 pi I. Now, what happens if I run this guy in reverse? Well, we already know what the answer is. If I run it in reverse, I get minus 2 pi I. So you might say, well, so some of you know topology, right? And you might say, well, okay, Cauchy's theorem, let's make a false argument here, okay? Let's prove that 0 equals 1. So you might start by saying something like this. And not too long ago, I had a friend, very smart guy, who made the exact same argument. Turns out it's wrong. All right, so here's my contour, right? But I'm going to run it in reverse. Okay, now the function f of z is 1 over z minus z naught. And here's z naught right in the middle. All right, now he said, well, you should apply Cauchy's theorem using the idea that actually the set D is everything outside the circle, D gamma. All right, but you can't apply Cauchy's theorem this way, right? So he said, well, okay, d gamma is everything outside of this, and this function is actually analytic on that d gamma. Therefore, when I integrate around this contour, I'm going to call this the gamma prime contour. No, actually, prime means derivative. Let's call it the tilde contour. If I integrate that guy, f of z, well, we already know what f of z is. It's just 1 over z minus z naught. He said, you should get 0, right? Is that right? No, you can't apply Cauchy's theorem that way.
It's not simply connected.
True, and it's not, yeah, and it contains infinity, right? Which is a kind of weird point. Well, we stated the theorem in such a way that this guy here had to be a bounded set also, okay? So if
Most of the assumption actually.
yeah, right. So this is not true, right? This is patently false. Oops, that's weird. Okay. Now, why is it false? Well, it's false because it's false, but we also know that gamma tilde is just equal to minus gamma, right? So we should be able to see that minus gamma of 1 over z minus z naught, well, that's just should be minus 2 pi I, because we showed that the integral around gamma is 2 pi I, so the integral around minus gamma should be minus 2 pi I. Does everyone see that? All right, so this argument here is wrong. So let's show that actually. If we run the contour going the opposite way, we already know what the result should be. You should just get the minus sign, but we can show it. We can show it by doing the calculation. So if we run the contour clockwise around the point z naught, then we can use this as our expression of the contour. In fact, I probably should have said this is gamma tilde, okay? Because it's not the same as that previous gamma. Well, this contour really is the reverse running contour. Oh, that's weird. No, I don't want that. I mean, that's okay, but okay. So this contour runs in the clockwise direction. It starts here and it ends there as well. Okay, around the point z naught. All right, so by definition, this integral should be integral from 0 to 2 pi in t. You simply replace gamma by this contour here, the value of the contour, and then you have to take the time derivative of that contour. And so that springs this minus I term. So you get a minus ri e to the it. So you get similar cancellation as you did previously, right? That guy cancels with that, r cancels, but I get a minus I that doesn't cancel with anything. So it works out the way you would think. So these results really, it's really important to keep in mind that most of these results you need to keep in mind or be careful about running the contour in the right direction. Okay, you need to think about the contour running in the counterclockwise direction. Then d gamma is everything contained inside of that contour. Okay, so the direction that you run the contour is often very important. Okay. Now, that was a neat little result, this guy here, right? But we also, how does this relate to this result? Well, this result, f was analytic. So the entire integrand was analytic. In this guy, the integrand is not analytic inside of D because there's a singular point here. Okay, it's not differentiable at that point where z is equal to z naught. So what if we combine these two facts? What in the world do you get in that case? you get something called Cauchy's integral formula. So if I integrate over gamma, so again, this gamma is going to be counterclockwise oriented. Doesn't have to be a circle in this case. So there's my gamma. It's running in the counterclockwise direction. Z naught is contained inside of this set D gamma. Here's D gamma. I have to have some sort of parent set. So there's my parent set D, where everything is nice. The function is analytic inside of D. Here's my D gamma. It's bounded by, it's a set bounded by this curve, this contour, using the right-hand rule, okay? If your fingers curl around the curve in this direction, your thumb points up in the plane, and therefore the set D gamma is everything on the left-hand side of that curve. Okay, not over here, okay? So it's just how do you define inside versus outside? You define inside versus outside by the right-hand rule. Same as in physics, right? All right, so assume that gamma is a simple, smooth, closed, counterclockwise oriented contour. D gamma is this set. Then if Z naught is any point inside of D gamma, it has to be a point inside of D gamma, then f of Z naught is equal to 1 over 2 pi I integral over gamma of f of Z over Z minus Z naught. Now, let's look at a very special case. Suppose that f is just equal to the function 1, everywhere equal to 1. Okay, so what do we get in that case? If f is equal to 1, that's an analytic function. Its derivative is just 0, fine, but it's analytic. And so what we know from that previous calculation we just did, this guy here, we should get that. But we should recover that with this case as well, right? As a sanity check. So if f is equal to 1, I should get 1 equals 1 over 2 pi I integral over gamma 1 over Z minus Z naught dz, right? Which is 2 pi I equals integral 1 over Z minus Z naught dz. That confirms the calculation that we had previously. All right, now I'm not going to prove this, but it's kind of a combination of that last fact with Cauchy's theorem. That's the proof. Okay, it's a lot more complicated than that, but not too much more complicated than that. Now, what this let's focus not on the proof of this, but focus on what it says. So it says that the function evaluated as point Z kind of depends on its values all the way around the boundary. So in other words, it's saying that the functional dependence on Z can't be independent of the functional dependence of F along this boundary. Somehow these two things are interrelated. Okay, they're interrelated precisely through this result. Okay, so the functional dependence at Z naught depends on the functional dependence along the boundary of the set that contains it. So that's Cauchy's integral formula. An extension of this, a generalization, if you will, is Cauchy's integral formula for derivatives, which says the following. And it's quite remarkable, I think. Suppose that D is an open, simply connected, bounded set. F is analytic on D. That simply means that F has one derivative on D, as far as we know so far. Assume that gamma is a simple, smooth, closed, counterclockwise oriented contour, and define D gamma to be the set enclosed by gamma, whose boundary is gamma. Then for any point Z naught inside of D gamma, and any n that you like, any integer n, f is n times differentiable at z naught. Okay, f is n times differentiable at z naught, and we have a formula for the derivative at a point z naught. So the picture is we have this set D. We know that f is analytic on D. We have a contour. It's counterclockwise oriented, and we have a point inside of it called z naught. Well, if we know that it's 1 times differentiable at on D, then it turns out that any point in the interior of D you can show from this simple result, or from this complicated result, that I have as many derivatives as I like at the point z naught, and I even have a formula for the derivative given by this. Okay, so again, I'm not going to prove this. It's a complicated proof, but it's a remarkable result. All we need to assume is that f is 1 times differentiable, and it turns out it's n times differentiable at any point in the interior. All right, so let's see how this this formula can be of use to us when we do calculations. I mean, I suppose that there's a few ways to look at this result. One way is, well, it tells you something marvelous about the function. That is, if it's 1 times differentiable, it's any number of times differentiable that you like. But another way you can view this result is, well, it's a formula that you can use to do computations, right? So let's do an example computation. Now, again, remember I said it's important that we understand that the contour has to run in the counterclockwise direction, and it's stuff inside of this guy that's important, okay? Namely, this point Z has to be inside of this set D gamma. And notice that where Z naught appears, so here, it's this point in here, it appears here, and it appears here, okay? And it's the only point of singularity of the integrand. Does everyone see that? It's the only point of singularity of the integrand. The integrand is otherwise not singular, at least inside of d gamma. All right, so suppose that gamma is equal to e to the it. Okay, for t equals going from 0 to 2 pi. That's an easy picture for us. Using Euler's formula, it's easy to see that this guy is a contour which starts here and makes a circle of radius 1. Okay, and it's surrounding the origin. This is the complex plane. So this is the imaginary axis, and this is the real axis, RZ. Okay. As I said, it's a smooth, simple, closed, counterclockwise oriented curve of radius 1 surrounding the origin. And let's consider this integral, okay? And let's see if we can't use Cauchy's integral formula for derivatives to calculate this integral without doing a lot of work. So normally when we would do something like this, we'd have to substitute in gamma for everywhere you see z, do a complicated expansion. We'd have to take the derivative of gamma with respect to t and calculate that very complicated integral with respect to the parameter t from 0 to 2 pi. All right, so let's define f of z to be equal to z plus 1 over z plus 4. So this function is a nice analytic function, except at the point where the denominator is equal to 0. When the denominator is equal to 0, this guy has problems. It has a singularity there where it's definitely not going to be differentiable. It blows up. And so it's not going to be analytic at that one point. So let's put that on our graph or on our picture here. So whenever z is equal to -4, that's maybe over here. Okay, z equals -4, bad things happen for that function z. Okay, otherwise the function z is analytic. You can, so by the way, all of the differentiation rules that you know and love from real land work for things like this, right? Rational functions. You can use the quotient rule, you can use the product rule, things like that. You can use chain rule. So F has no singularities inside of the set enclosed by gamma, namely that set we called previously D gamma. There's no singularities in there. So how does that help us compute this integral? Well, notice that this is not all of the integral here. Notice that the integral, or sorry, the integrand can be written as f of z over z cubed. F of z over z cubed. Simply multiply it out, you'll see that that gives you the integrand. So what we've done is split up the integral, or the integrand, into something which is analytic inside of d gamma, and a part which is not analytic, okay, because this function 1 over z cubed is a problem area, okay, or a problem function. But I'm going to write this as 1 over z minus 0 quantity cubed. What does that tell us? That tells us that the point z naught is equal to the point 0. So namely, our point of singularity is right here at the origin. So let's go back one page, or maybe two. One is all we need. Let's look at what we need in terms of this formula. We need this integrand to be something like z minus z naught to some power n plus 1. Okay? Well, we have that. We have z minus 0 to the power 3. So that tells us that our n is equal to 2. The n is equal to 2. All right, so we're really just looking at this guy. Well, that's okay. We can throw this stuff to the other side. We can just throw that to the other side and just examine this guy. Well, that's basically what we've done, right? So we rewrite this guy as, if I just put an equal sign here, I'm writing this as f of z, where it's f of z is this rational polynomial, divided by z minus 0 to the third power. But I'm going to write that in a more descriptive way. I'm going to write this as to the 2 plus 1 power. So that tells us that n is equal to 2. Right? Z naught is equal to 0, n is equal to 2. Now we can apply Cauchy's formula for derivatives. So the theorem tells us that this integral, which we've rewritten in this form, right, where n is equal to 2, z naught is equal to 0, has to be equal to 2 pi I over 2 factorial times the second derivative of f at 0. So that's just unpacking Cauchy's formula for derivatives using the information that we have from this integrand. Now, again, the complex differentiation has the same rules that real differentiation has for the most part. If I want to take the derivative of f being a rational polynomial, I'm going to use the quotient rule. The first derivative just gives you 3 over z plus 4 quantity squared. So you can try that out. Okay, the quotient rule is just going to give you 3 over z plus 4 quantity squared. Just try it out. And now for the next integral, I can do the second derivative. Sorry, I might have said integral a couple of times. I meant to say derivative. For the second derivative, just apply either the quotient rule again or the power rule in this case. You can apply power rule combined with chain rule if you like, right? So the way I would do that is I would write f prime of z is equal to 3 times z plus 4 to the minus 2 power, right? And then I could just use a combination of the power rule and the chain rule. And I get the second derivative is just minus 6 over z plus 4 quantity cubed. So there's my formula. All I have to do now is plug in z equals 0 and evaluate. So my integral turns out to be 2 pi I over 2 factorial, which is 2. If I evaluate the second derivative at 0, I should get minus 6 over 4 cubed. And that works out to be -3 pi I over 32. So whether you view this awesome result as a simple computational tool or a powerful result which tells you something marvelous about complex analytic functions, either way, it's a powerful tool. Questions before I move on? Anybody? Okay. Everybody's cool with that? So I can use that last result to prove Taylor's theorem for analytic functions. In fact, I wouldn't call it Taylor's theorem. Taylor's theorem I always view as being when I do a finite power series approximation or a finite polynomial approximation, Taylor polynomial. This is a bit different. Suppose that D is an open, simply connected, bounded set, and F is analytic. We already know now that that means it's infinitely differentiable inside of D. For any point Z naught inside of D, F is differentiable at Z naught to any order that you like. That's given to us by Cauchy's integral formula for derivatives. And the new part is that F can be written as an expression, as an infinite series expression, K equals 0 to infinity, Kth derivative evaluated at Z naught over K factorial, Z minus Z naught K. So this is the typical power series expansion for a function that you've seen from real land. But it turns out that if F is differentiable one time, then it has a power series expansion on D. If F is differentiable one time at every, so just plain old-fashioned differentiable on an open, simply connected set, bounded set, then it has an infinite number of derivatives on that set, and it's equal to its power series expansion. The same is not true in the real world, okay? The world of real valued functions. F could be an infinitely differentiable function in real land, but not equal to its power series expansion. Okay. Moreover, this power series converges absolutely on a disk. So the disk that we're interested in is this set D is some complicated looking thing. And we choose any point Z inside of that guy. The disk that we're talking about is the disk that fits nicely inside of there. Okay. It can't cross over and go into this region. Okay. Can't go outside of D. So it's equal on that disk. So that's namely this disk here, and the power series converges absolutely on that disk. Does everybody remember what absolute convergence means from your calculus days? Okay. Well, now I can talk about the method of steepest descent. So I'm not going to get through all of this section. I'll start my explanation of method of steepest descent, and then we'll have to come back to it next time, I'm quite sure. But again, method of steepest descent is not new for us in terms of the asymptotics. The asymptotics is going to be dictated by Laplace's method, okay? Or, well, Laplace's method, which is basically described by Watson's lemmas, right? Watson's lemma for integrals of the first kind and for the second kind. So there isn't going to be any new terms of asymptotics. This is all going to be a reinterpretation of how to use those asymptotic expansion methods in the lens of a contour integration. I'm going to be interested in contour integrals with a large parameter. Okay, so contours or contour integrals of this form. I of lambda, lambda is our large parameter, is an integral over a contour, chi. That chi can be anything, but so for now, we're not going to worry about it, where the integrand is equal to h of z e to the lambda rho of z dz. Now, I need to require a couple of things to apply my theory. The first one is that, no, not theory.
Theory. Use Y out.
There we go. Theory, not Siri. Theory Okay,
That happens to me a lot.
really, saying
Especially
the
at
word,
lecture 4, and then the lecturer say, "Oh, why do you activate theory?" I say, "No, I don't want to."
oh, you know what? I think I forgot to, it's my,
No, it doesn't matter.
oh, it doesn't matter. Okay. I thought maybe if I set my do not disturb, you know who won't disturb me, but. And there, when you're at home, when I'm at home, I'll say certain words which sound like Alexa, and that'll activate, you know who. Okay, so the integrals that I'm going to be interested in are those of this form. The integrand is of this form, h of z e to the lambda rho of z. You might notice by now that all of the integrals that we've talked about are of this form, or can be realized of this form. They always have an exponential times something else, and the exponential has a power which looks like this, either lambda or lambda squared times some function. Now, what we're going to assume is that rho is an analytic function on some bounded, open, simply connected set D, which contains this contour chi. And we're going to also assume that h of z is analytic in D. So the picture is, I don't know why my set Ds always come out looking like a turtle or a kind of like a, I don't know, like a,
Starfish.
no, I was thinking more like a, you know, the eyes there and
A pony.
dinosaur. Yeah. Yeah.
Rat.
Polar bear, you say?
Pony.
Pony. Okay. Yeah, something. Anyway. There's my set D. And this contour is not a closed contour. It's just some contour from some point Z0 to Z1. That's my picture. Inside of the set D, H is analytic and also rho is an analytic function. Okay, they're both complex functions in general. Now, in terms of a definition or variables that I'll need later, I'm going to define phi to be the real part of rho and psi to be the imaginary part of rho. So again, if you don't like these symbols, the handwritten symbols are like this. Okay. Now here are, so this means that based on our definition, that rho is just equal to phi of z plus I psi of z. Now here I need to make you aware of an abusive notation which I'll make over and over again. So sometimes when I find it convenient, I'm going to think about phi as being a complex function or a function of a complex variable. Same with psi. And other times I'll write psi as a function of the real variables x and y, where x and y are the real and imaginary parts of a point z. Okay, so just keep that in mind. I'm constantly going to abuse notation by saying that phi of xy is equal to phi of z whenever z is equal to x plus iy. Some of you might think or look at me strangely by saying that that's not an abusive notation at all, that that's just the most natural thing you could do. And I say, well, this is a function of two real variables, and this is a function of a complex variable. How could they possibly be the same? It's truly an abusive notation, but it's a convenient one. Okay, so here I'm thinking about them as being functions of z, and later on I just ping pong back and forth all the time. So don't lose your head. So here are the elements of steepest descent that we need. I'm going to show you again and again through pictures what's going on here. So this long list will get replaced by a picture in your imagination, I think. In the simplest setting, we're going to seek a closed contour gamma in D So D is the set which contains chi, and hopefully it'll contain this gamma as well, such that the contour gamma is piecewise smooth, and it traverses chi as its first segment. So gamma is going to look like it's going to be, so what I mean when I say when I add contours together, that means you run chi first, then you're going to run gamma 1 afterwards, then you run gamma 2 after that, and gamma 3. So I'll show you a picture so that it's concrete in your mind. Now, what's really important about the method of steepest descent is that I really want to construct this contour not in some arbitrary fashion. And first of all, even before I get to that, I should probably say something about, well, why am I constructing another contour gamma in the first place? Well, we'll get to that a little bit as well. But what I want to make happen definitely is that I want psi to be equal to a constant on gamma j equals 1 and 3. Again, I'm going to show you the picture, and the picture will bring this home. So I want psi, that's the imaginary part of rho. I want that guy to be a constant on certain segments of this new contour that I'm constructing called gamma, namely segments 1 and 3. Now, psi is not necessarily going to be constant on this contour gamma 2. That contour gamma 2 has a special name. It's called a bridge contour. And you're going to see it. It makes a little bridge in our diagram, and so it'll make sense. Now, even though the bridge contour, I don't know that psi is going to be constant. There's nothing I really know about the function or the integral over this bridge contour. What I do want to know is that when I integrate over that bridge contour, the result is somehow controllable. Okay, that I can handle what's going on with that, maybe by an estimate. In fact, what's usual is on the bridge contour, I'm going to show that contribution becomes vanishingly small as I adjust where that bridge contour is. So the idea is on the bridge contour, most of the time you can just think about it. It's just going to become vanishingly small to the point where you won't have to worry about it. Now, for the contour segments where I have psi being constant, that's contour segments 1 and 3. What I want to do is construct them in such a way that psi, sorry, not psi, but phi function. Phi function is the real part of rho. I want phi, when you evaluate them on those contour segments, gamma j equals 1 and 3, to have a maximum at the point where gamma j connects to the original contour chi. This one is hard to understand until you see a picture. So in other words, I want phi to be decreasing along gamma j for j equals 1 and 3 as we move away from chi. All right, so here's the picture. Nope, sorry. Here's the picture. We'll come back to that in a second. All right, now, before I get to the picture, let's evaluate what we've done through Cauchy's theorem. All right, so I have this original contour like this. I didn't want to make that straight, but okay. There's chi, and I'm going to make a new contour called gamma, where I run chi as my first stretch. Then I run another leg, gamma 1. Then I run a little bridge. That's called gamma 2. And then finally, I run gamma 3. Okay, I want to make something a little more interesting than that. So gamma 3 might be like that. So that's gamma. You run chi first, then you run gamma 1, then you hop over this little thing called a bridge contour, and then you ride gamma 3 back to the starting point. So that means that this gamma, zip, 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 is a closed contour. It's piecewise smooth. In this case, it's simple. It doesn't intersect itself. but it can later on intersect itself. Now, here are my constraints. I want psi, when I evaluate it on gamma 1 and gamma 3, what did I say? I want psi to be constant on those. I want psi to be constant on those if possible. And I want phi to be decreasing as I go along gamma 1 and gamma 3, but moving in the direction away from chi. So in other words, when I go in this direction along gamma 1, I want phi to be a decreasing function. And when I go this direction along gamma 3, because it's moving away from chi, I want phi to be decreasing. Okay, so I'll draw this on a picture momentarily. But before we get to that, what does Cauchy's theorem say? Well, the integrand is everywhere complex analytic. So as long as this contour is closed and bounded, then I know that the integral over that contour is always going to be 0. It's going to vanish, right? That's what Cauchy theorem guarantees us. But now I can break gamma into a bunch of contours, right? So I can break it into chi, then gamma 1, gamma 2, gamma 3. So, and I know that I have this contour is equal to, or this contour integral is equal to 0. But I can write that in a simple way or different way. Okay, I'm going to write it as, I'll skip the stuff in here. That's just going to be, because I'm running chi first, then I'm running gamma 1, not dx. We're living in complex land. Then I run gamma 2 next. That's the little bridge contour. There are things inside of here. And then finally, I run gamma 3. All right, but this is equal to 0 by Cauchy's theorem. So that means I can say that this guy is equal to this plus that with a minus sign, right? That's what I have here. The contour over chi is just equal to the contours over gamma 1 and gamma 3 with a minus sign, minus the contour over gamma 2, the bridge contour. Now remember, on these contours gamma 1 and gamma 3, psi is a constant. Psi is a constant when I plug that guy in. So when I run it over that part of the contour, out is going to pop that constant value Cj. Okay. In fact, what pops out is E lambda I Cj, because the imaginary part is just the constant Cj along gamma 1 and gamma 3. So that guy comes out, and the integrand simplifies a little bit. This integrand doesn't simplify, but that's okay. I imagine that this guy is going to just become vanishingly small as I adjust this bridge contour slightly. Well, not slightly, but I'm going to shove it off to infinity, actually. Now, minus gamma j is just the same contour as gamma j, but it's just run in reverse direction. That's the rule. All right, so we're going to have to pick up. We're going to stop here and pick up next time, but let me run over just the basics again. The original contour is along chi. We've constructed gamma 1, gamma 2, and gamma 3 so that I get this closed contour gamma. The integrand is analytic on any set which contains this guy, because the parts of it are analytic everywhere. The integral over all of gamma is just going to be 0, so I argued just a moment ago that the integral over the closed contour is 0, and so that tells me the integral over chi is now equal to these integrals. Now, what did I say about these integrals? Along gamma 1, psi is a constant, and I'll write this on the picture next time. Psi is a constant. We're going to call that C1. And along gamma 3, psi is also constant. We're going to call that C3. Along the bridge contour, well, we're not going to worry too much about that. We're just going to hope that that guy can become vanishingly small as we kind of push that guy off to infinity. We're going to push it out there. The other thing I want to mention is that phi, the real part of rho, has to be decreasing as I move away from chi. Okay, phi has its maximum at this point, and then it's decreasing along gamma in this fashion. Likewise here, the phi function, which is the real part of rho, is going to have its maximum here, and then it's going to be decreasing along gamma 3 as we move away from this original contour. Okay. Now, how do I construct these contours where the real part or the imaginary part is constant and the real part is a decreasing function? We'll talk about that next time. And I will see you guys next time. If you have any questions, shoot me an email. You can come up afterwards. But I'm going to let everybody in virtual land go. If you have a question, you can come up and ask it after class. And I'll see you guys next time.